is a beautiful example of resonances in mechanical system. Let's look at this one more time. You can see when the natural frequency of the string equal to the frequency of the external force imposed by the vibrator, the string will resonate, and resonance will occur when the natural frequency of the string is equal to the frequency of the resonator, equal to 2 times the frequency of the vibrator, equal to 3 times the frequency of the vibrator, and so on. Well, that's what you actually saw in here. By the time the reflected wave gets back, the second wave is ready to advance, and that is where the agreement occurs. So the energy of the second wave gets reinforced with the reflected wave, and therefore you have the reinforcement and the amplitude increases. You have a big wave, a resonance, is that right? An agreement of frequencies. Now, when this happens, the string is said to resonate with the frequency of the periodic force. In other words, the frequency of the periodic force agrees with the frequency, the natural frequency of the string. That is when resonance occurs. There must be agreement between natural frequency and the external periodic force. All right? That is what resonance is. Let's now look at resonance of air columns. Can air columns resonate? What does that mean? Resonance of air columns. Let's take a look. Air enclosed inside a tube can be made to resonate with an imposed frequency. Now, how can we do that? Let me see if I can show you a couple of examples where air columns can be made to resonate with an external frequency. Now, is there a teenager who has not done this? Now, watch this. This is the cap of a pen, and now, haven't you done this? Well, if you were a high school student and if you wanted to disturb your teacher while teaching, this is what the most common thing among teenagers is. While the teacher is very seriously discussing Newton's law of motion, the student goes, well, the teacher looks back, who did this? I don't know. Nobody knows. Well, it is a good example of resonance of air column. The column of air enclosed inside this tube has a natural frequency. Now, your lips can produce a varieties of frequencies. If one of those frequencies equal to the natural frequency of the air column in here, then the column of air will resonate. You see, that is what you hear, the loud sound. If a frequency does not resonate, no, yes, that particular frequency resonated, and the column of air vibrated with large amplitude, forming stationary waves. Now remember, stationary waves are formed by the formation of nodes and antinodes. So air column inside vibrates, forming nodes and antinodes. All right, let's review a bit on stationary waves. Tell me, what is the distance between 2 adjacent nodes of a stationary wave? The distance between 2 nearest nodes is half of a wavelength. Is that right? Yes. So, if you have one complete segment, the length of that one complete segment is 1/2 of a wavelength. We're going to use that in this lesson. Now, I have another tube here. Can you see this? There I have a tube, and a column of air is enclosed in there, and can I make that column of air resonate with an imposed frequency? Well, I can use a tuning fork, is that right? Vibrate the tuning fork and keep it at the mouth. If the frequency of the tuning fork equal to the natural frequency of the air column, in other words, by the time the first wave energy goes down the length of the tube and returns, you get the new wave produced. That is when resonance occurs. That is, the natural frequency agrees with the frequency of the imposed force. Now, do you hear a loud sound here? I don't hear one, which obviously means there is no resonance. The natural frequency of this air column is not equal to the frequency of the tuning fork. Alright, let's try another tuning fork. There is one. Well, I can hear it's louder than before, but I'm not really satisfied, because if that air column resonates, did you hear this, the resonance of this? Look at this. That's a very loud sound. Now let's try another tuning fork and see if we can get a better result. Well, certainly this is better. So you can now see the air column is now resonating with the frequency of this tuning fork. And the frequency of this tuning fork is written on it, 440 Hertz. So what is the natural frequency of the air column inside the tuning, inside this tube? It is 440 Hertz. That's right. So a column of air can be made to resonate with the frequency of an external force. So a column of air enclosed in a tube has a natural frequency of vibration, and this air column can be made to resonate with the frequency of a tuning fork like this. Set the tuning fork vibrating, and if the natural frequency equal to the frequency of the tuning fork, the air column resonates, producing a loud sound. When resonance occurs, a loud sound can be heard because of the increased amplitude of vibration. Now, when this happens, I told you there are nodes and antinodes formed inside the tube. Now, the particles at the mouth of the tube has the maximum amplitude. You see, at the mouth of the tube, particles cannot be at rest. That means a node can never form at the mouth of the tube. The mouth of the tube will always be an antinode. In the same way, at the fixed end, you cannot have maximum displacement. The fixed end will always be a node. So, if the tube is closed at one end, that closed end will have a node, and the open end will have an antinode. So the open end is an antinode, the closed end is a node. And you can have nodes and antinodes in between depending on the mode of vibration. It can be the mode, maybe the fundamental mode, it can be the higher modes of vibration. What do you call the higher modes of vibration? The harmonics, the higher harmonics or overtones. You see, the vibration of the air column inside a tube is very similar to the vibrations of a stretched string. You have the fundamental, the second harmonic, the third harmonic, and so on. We'll take a look at these as we go on. The higher harmonics of air column can also be made to resonate with the frequency of the periodic force. In other words, the air column will resonate not only a frequency equal to its natural frequency, it will resonate with a frequency equal to twice its natural frequency, 3 times its natural frequency, and so on. That means there are higher harmonics. Let's now talk about a closed tube. A closed tube is the one I just demonstrated. Do you remember the tube I just showed you? The tube I just showed you is this, which is open at one end and closed at the other. So this is a closed tube. Now what is the specialty of a closed tube? A closed tube is closed at one end and open at the other. That means this is the fundamental mode of vibration of a closed tube. Now, in the fundamental mode, you have an antinode at the mouth of the tube, a node at the closed end. The open end will always be an antinode, and the closed end will be a node. In the fundamental mode of vibration, you have a node at the closed end and an antinode at the open end. Now tell me, if this is the fundamental mode of vibration, then how many waves are contained in the full length of the tube? The mouth of the tube is an antinode. The closed end is a node. What is the distance between an antinode and a node? Do you remember that one? Let me just refresh your memory just one more time. Well, if this is a stationary wave where you have node, 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 antinode, antinode, this full length of two loops is one wavelength. You recognize that? One wavelength contains one crest and one trough. That means for a stationary wave, the length of two full segments is a wavelength. That means the distance between two alternate nodes. What will be the distance between two nearest nodes? The length of one full loop or one full segment is half of a wavelength. Tell me, what is the distance between a node and an antinode then? It is a quarter of a wavelength. So inside this tube, in its fundamental mode, what we have is a quarter of a wavelength. The distance between a node and an antinode is a quarter of a wavelength, lambda by 4, and this is the whole length of the tube. So the length of the tube now is a quarter of a wavelength. Let's write that equation. L, the length of the tube, equal to lambda by 4. Therefore, wavelength lambda equal to 4L. In the fundamental mode of vibration, the wavelength of the stationary wave inside the tube is 4 times the length of the tube. Alright, let's say F0 is the frequency of the fundamental. Can you then write an equation of the frequency? Well, frequency equal to wave speed divided by the wavelength. Is that right? If F0 is the frequency of the fundamental and V the speed of sound in air, then F0 equal to V over lambda. And what is lambda equal to? Lambda equal to 4 times the length of the tube. So fundamental frequency of the air column in a closed tube is V over 4L. A very important relation. Alright, let's now look at the next mode of vibration. What will be the next mode of vibration in a closed tube? I don't know whether you can actually see this. Now, in the next mode of vibration, let me just reset my camera a bit. Alright, I want to refocus the camera a bit to show you the picture on the right. There we are. Okay.